Hello, welcome to lesson 3. This is regression with different constants. This is an important lesson in which there are a lot of new ideas and very useful ideas, and this is a long lesson but has a lot of substance. I hope that you will like it very much. Thanks. The introduction that I want to make you is that when homogeneity is rejected, a simple and useful way to capture heterogeneity is to use different constants for different individuals. So the idea is we may have a lot of neglected relevant variables, and what we can do to deal with them is to use different constants. Different constants is going to be a very useful idea in econometrics, and it's going to be very useful in applied work. Using different constants for different individuals can be useful to capture the importance of individual variables that do not vary across time, the importance of and effects of time variables that do not vary across individuals, and variables that vary across individuals and time. So this is one idea, a very important idea, and that is that heterogeneity is going to be captured, subsumed in the different constants. Also, numerous omitted variables that vary across time can be captured by the different constants, and that is very important to be able to deal with the problem of omitted variables. Omitted variables, which is a very big problem, is going to be alleviated by the use of individual different constants. And then in this part you see again that omitted variables do not vary over time, effect of variables that do not vary in the cross section, so they can capture many variables that would cause problems when not accounted for. Let's see the first basic model for the using different constants. That would be the fixed effect model, and in this part you say OLS with dummy variables, because that is going to be the estimation technique, the estimation technique of choice. So here in the upper part, the title, you have model and estimation technique. They are different. In this case, one estimation technique is the most preferred for a fixed effect model, but they need not be confused one with the other. So if we go back to the main formula that we were talking about in the previous chapters, see that we have a YIT equals alpha sub I to the star plus beta prime xit plus URT. Again, alpha sub I star is a scalar, the number, which is different for each individual, and beta is a vector of 1 by capital K unknown constants that do not vary across I and T, because they are the same. That is the homogeneous part of the model, while the alphas are the heterogeneous part. Again, this is the explanation that we have, and we assume that for simplicity that there's no correlation between x's and the errors, so that makes up for the possibility of using the Gauss-Markov theorem to justify the use of OLS in this particular setup of the fixed effect model. Using a constant dummy for each individual, we can estimate by ordinary least squares, which is the best linear unbiased estimator, and that therefore the Gauss-Markov theorem applies. And if the Gauss-Markov theorem applies, this is the most efficient estimator that within the class of estimators which are linear and unbiased. So this is a good properties that OLS has for the fixed effect model. Good properties make it decidable. Let's now look at the formulas. This first formula is how to go from observable to unobservable. We have observables of x, x bar, y, y bar, all those we have data, and those are the observed heterogeneity, and we have data on those, and what we do is we combine those in an optimal way to get good estimates of the parameters that we do not observe but we care about. If you look at the formula, this is pretty much as you have seen before, x prime x to the minus 1 x prime y. Now it is more complicated because it has an inside summation that goes from 1 to capital T. That is a summation for one individual, and then for one individual, and goes from 1 to T within each individual, and then there is an outside summation that goes from I to N, and that is summation across all the individuals. So first we look at the variation within each individual, and then we sum it along all the individuals. This is the same as x prime x to the minus 1 x prime y, the same idea. So the idea is basically we want to have a partial correlation between each x and y. So we want to disentangle the individual effect of each x on y. And that would be the estimator, which is called the OLS dummy variable estimator, but it's called also the covariance estimator, and that's why we have a beta hat CV there, covariance. It is a simple estimator, and the way in which it is actually computed is well done within Stata, so we don't have to worry about those details. Then the alphas. The alphas are very important. The alphas are like your grandmother, or someone who is very important, but you don't necessarily want to be leading with them all the time. So the alphas are estimated in a second step. First you have the beta hat estimates, and then you use them to construct by difference the alphas, alpha hat star sub I, which is down there in the formula right here. So we have the two components, alphas and betas. They are estimated by ordinary least squares, and Stata does it for you automatically. You don't have to know the details, but you have to understand what it is doing. Then there are some other formulas that I don't want to look at this particular point in time, because you're not going to be going to for a PhD in econometrics, so it is really not necessary to go through this, so we just skip 10. If you look at page 11, this is the same estimator as before, but using that new Q matrix, which we are not going to deal with again today. So this is something that you have to remember more or less, that there is another way of writing the same estimator. That's all you need. The properties of the covariance estimator are important, and they are something that you have to understand well. The first one is existence. The estimator exists for a large variety of situations, and it gives you an answer. Then a second property is that the answer is unique. So there's only one answer to the question of what are the betas and the alphas. A third property is unbiasedness. Unbiasedness means that on average the estimator coincides with the true value. It is a small sample property, it is an interesting property, but it's not really a very compelling property, because the compelling property is the next one. Consistency. Consistency is telling you that the estimators are going to get as close as desirable to the true values betas when you have a large enough sample in terms of n, capital T, or both. So this is the property of consistency. This is a property that is important, necessary for all usable estimation techniques, and it is necessary to understand that the idea is that it is an approximation to the location of the set of parameters beta, which are again unknown. They are known, but the estimator that you are using has the property that when you have a large enough sample, that they approximate well, as well as desired and necessary, the true values of the beta parameters. Then there is another property here, which is efficiency. Efficiency is important because efficiency is not about the location, it's about the dispersion of the estimator. And the idea is that you want estimators that are close to the true value in a sense that they are close to each other, they don't fluctuate very much, they are precise, they are efficient, they have little variance. So the importance here is it is a property of the variance of the estimator, and it's telling you that it is minimum variance. The Gauss-Markov theorem in this particular case applies, and it tells you that it's the best linear unbiased estimator. So that is the motivation for using OLS in this particular model of different constants model. Then there are more things that you may want to know or not. Let's forget for the moment about the variance covariance matrix, which is the one that you have there. Then it is important to know that the estimates of alpha, the alpha hat sub I star, are unbiased in the sense that expected value coincides with the true value, but they are not consistent. So they may be unbiased, but consistency, which is an important property, is not shared by this estimator of the alphas, because it is only consistent when there are a lot of time observations. Capital T tends to infinity. So we have seen first the fixed effect model and its associated estimator. Now let's look at the second model, which is the random effects model. The random effects model is called also error components model, and the idea is that now we are dealing with the alphas like if they were random, and in that case we have in principle three components of the error, which is the alphas, individual component, the lambdas, the time component, and the u's, IT, which is the common component. So let's, in the last two lines, we have a lot of inequalities, a lot of restrictions, and what that is doing is making it easy for us to deal with the problem. They are saying everything is fine, no problem with the alphas, lambdas, u's, no problem with the correlation between alphas and lambdas and u's. So the second two lines are telling us no problem, don't worry about these problems. So this is what it's saying, what I just told, no problem in the with the errors, no correlation between errors and regressors. That is what it says here. So we're isolating the problem and leaving just the elements that in which we want to focus on. The variance of yt conditional on xt, given all those assumptions that we have seen, is the sum of the variances. Sigma squared sub I equals sigma squared sub alpha plus sigma squared sub lambda plus sigma squared sub u. And what they do, because of all the simplifications that we have done, and the equation now can be written in a very simple way, just using deltas instead of betas and alphas, and simplifying also the error term. So this is going to be a simple way of writing the equation in this particular case. Now we are getting into the core of the problem here. The core of the problem is that now the variance covariance matrix of the error is not as usual sigma square u times I sub t, but it's bigger, it has another component. When it has another component, in this particular case, what is happening is that we have serial correlation. We have serial correlation in the errors of each individual, and that means that if we estimate by OLS, the estimation is not going to be efficient, but if we use some other more sophisticated technique, we are going to be able to estimate well, even better than by OLS. So this is what I just said, and the idea is that you can estimate now the model, the variance component model, in different ways. One of the ways in which you can estimate the model is using the covariance estimator or the dummy variable least square. That is the first estimator that we checked in this lesson 3. So we can estimate it as we did in the fixed effect model. We can do it, there's no problem, but the main drawback that we have is that now the estimates are not efficient, they are consistent but not efficient. Under random effects, the beta hat covariance is not efficient. In case of the random effects, it would be optimal, more efficient, more precise, to estimate using generalized least squares. That is, taking into account the serial correlation to be able to fix it and to obtain estimates that are better, more efficient than in the previous case. Between groups estimator. Now we are dealing with an additional estimator. We are saying, well, this idea of panel data allows us to construct many different estimators. So one of them is the one that we just saw before, which is the within estimator, and dummy variable least squares. That is the one that we saw. Now we are going to try something else. We are going to try an estimator that what it is going to do is just collapse all the observations for each individual in one observation. Take the average of the observations for each individual and construct one observation only for each individual. So if we had before n times t observations, so capital N times capital T observations, that would be the whole sample. Now we collapse it in the dimension of the capital T and have just capital N observations. So one observation per individual, per country, per firm, whatever. In that case, what we have is an estimator that after collapsing is very simple because it's just ordinary least squares. It is ordinary least squares, nothing new. So that would be the beta hat sub b. B means between, and the idea is that you only look at the variation between individuals and not the variation between within each individual. So that would be the between groups individual. This is interesting, and this is something that we want to deal with later. Now, in this point, estimation by GLS, the question is, well, we have seen two estimators. One is the within, looks only at the within variation within each individual. The other one is a between estimator, looks only at the variation between individuals. Both give answers, but typically the answers are quite different. So what do we do? What we do is we are going to combine the two sources of variation optimally to obtain an estimator that is going to be called generalized least squares, and that estimator is going to take into account both sources of variation. If you look at the sample, the equation that we have in page 22, we see here that we have the two previous equations, but they are just put together like a Frankenstein formula. The Frankenstein formula just picks the pieces of the previous two formula and puts them together. They don't leave anything out, so all the components are there, but let's see what is the meaning of this. Actually, you see both formulas are there, they are put together. The only new thing is the capital psi that you have there, that is somehow working as a connection between the parts of the two formulas. Capital psi you have in the lower part of the transparency is equal to sigma squared sub u over sigma squared sub u plus capital T sigma squared sub u alpha sub alpha. So now, what is that capital psi? This is essentially telling you the relationship of the variation due to the general variation of the model and the variation due to the individual variation of the alphas. So this is essentially like a way of telling you how to combine optimally the two formulas that we have seen. What is this formula, the big formula, doing? It is taking advantage of the structure of the variance-covariance matrix of the errors. It combines the within and between groups variation, and the resulting estimator is a combination of the within and between groups estimators. So that is the Frankenstein type of formula that I was talking to you, and that is so useful in applied economics. If we look a little bit in detail into the formula, we will see that, for instance, when psi is equal to 1 or is close to 1, then the GLS converges to OLS. And then when psi tends to 0, the GLS converges to the within estimator. So the important thing is, what is the typical value of capital psi? Capital psi is typically like 0.07, 0.05 or so. So typically the GLS is close to the within estimator. It's not very far to the within estimator. So that is in the typical value of capital psi in practice. Psi again is the weight given to the between groups variation. If capital psi is small, then the between group variation is not very powerful in this formula. So it says here that random effects model is an intermediate between treating all the effects as equal and treating them as all different. So it's a compromise. We don't need to look at these formulas. The only important thing is that the GLS variance is smaller than the covariance variance, and the GLS is more efficient than the covariance estimator, and that can be shown, but we are not going to see it in detail in this course. But it is important that that's the case. Okay, so now we have seen in the previous transparencies how we can employ like 3 different estimators for the random effects model. But now the big point is, how do you choose between a fixed and a random effects model? It is not trivial. If you have a very large sample in all respects, it shouldn't be problematic because the answers would be similar, but that's not the case typically. If you want to, if you're thinking about using a fixed effect model, then you would like to think about doing inference, which is conditional on the effects present in the sample. And that is important to know, and that is something that you may want to take into account. The random effects model, on the other hand, it's unconditional. So you try to infer things about the whole population and not only about the effects that you have in your sample. What you want is more appropriate in this case. In each case depends on the researcher. The researcher has to decide what is more appropriate, what is the question that he or she wants to answer. As I said, with large T, the estimation used fixed or random effects gives similar results. But typically, with relatively small capital T and large capital N, then the choice is not easy. The difference between the two equations is usually large. So the estimations have usually a large difference, and the idea is somehow you have to make a choice, and the choice is important. How do you make a choice in terms of theoretical considerations? Well, the fixed effect model is more appropriate when the sample coincides with the population. The individuals are important, and the inference is centered on the effects that are present in the sample. So we care about our sample and the small sample. The random effects model, on the other hand, is more applicable when you have a large sample from a larger population and you have inference that you want to make with respect to the population, not to the sample. And because the sample that you have is only a random sample and it could be something else. The basic idea here is why is that difference and why is that the difference is important. And one possible cause is that you have a specification error. A specification error in this particular case means that there is correlation between the observed heterogeneity, the X's, and the alphas, which are essentially the unobserved heterogeneity. In this particular case, I want just to show in this transparency 32 that this can be dealt with in a formal way, but we are not going to do it now. And the idea is that there may be differences. The next thing I would like to tell you is about the formulation of Moonlag, and the idea is that Moonlag, who is a researcher in panel data, criticizes the use of random effects, and he says that with economic data it is very common to have correlation between regressors and individual effects, so he proposes to use always the fixed effect model. So the fixed effect model, which is a interesting model, it can have important problems because in many cases important variables may be dropped from the specification if you use just fixed effect model. So it is problematic. But Moonlag sustains that if the correlation between effects and regressors could be corrected, the appropriate model would always be the fixed effect model. Again, this has problems. One of the many problems that it has is that it is only true for the linear case, not for the dynamic models that we will see in lesson 4, and also is not true for discrete choice model or random coefficient models. So this is an interesting idea, but not necessarily something that you want to entertain very seriously for the moment. Next, let me tell you about specification test. Hausmann is a very well-known researcher at MIT. He is an economics professor that has been working for many years in panel data. By the way, he is the supervisor of my supervisor, so I am like his grandson in terms of academics. He's a very nice person and very smart, and Hausmann wants to help a little bit you to decide whether to estimate by OLS or GLS a random effects model. So here we are thinking of a situation which is very different from the typical situations that you have seen before. Before, in most of the time, what you have to do is decide between two models using the same estimation techniques. Here, different. Here you want to decide between two different techniques for the same model. A totally different question. So the question here is, assume that you have a random effects model, and then you have to estimate. You have to estimate it as best as you can. So now, how can you do it? Well, the problem is that if the alphas and x's are correlated, then you don't estimate it well using GLS. If they are not correlated, you would estimate them well using GLS. But the question is, how do you know whether alphas and x's are correlated? You don't know. You don't know because the alphas in general are not observable, and you don't know whether they are or not correlated with the x's. So what, but in principle, the null hypothesis of the Hausman test is no correlation between alphas and x's. And the alternative is that there is correlation between alphas and x's. So under the null, we are fine with GLS. Under the alternative, we have to use OLS when estimating a random effects model. So we again look at the null hypothesis and alternative hypothesis, and again insist on the idea that under the null, generalized least squares is consistent, and under the alternative it is inconsistent. The covariance estimator is always consistent but inefficient under the null, and under the alternative is also inefficient, but it doesn't matter because it's the only one which is consistent. What Hausman does is he devises a procedure which is practical, which is going to measure the distance between the two estimations by OLS with dummy variables, the covariance estimator, and by GLS. So he's going to measure that difference, the Q hat equals beta hat CV minus beta hat GLS. He's going to look at that difference. In principle, that difference should be small under the null and large under the alternative. Using the famous lemma of Hausman that says that the variance of Q hat is the difference of the two variances, something which is not obvious, but it is very interesting and very practical in this setup. What he does is he constructs a Hausman test. He proposes the statistic M. If he says that if he should have called it H, he would be given a Nobel Prize, but he called it N, so it's not associated directly with his name. So what he does is he sets up this formula in which he's trying to measure the distance between the two estimations, Q hat in this case. He squares it, the distance between the two estimators, and compares it with the variance of the Q hat. In this case, what he's trying to do is measuring whether that distance, the vector of slacks there, is big or small. Under the null of no correlation, then the statistic would be small, and under the alternative it would be big. Under the null, it's going to be distributed as a chi-square with the number of degrees of freedom equal to the number of parameters tested, and under the alternative, this is going to be a non-central chi-square, so it's going to be big. The basic idea here is that a big value of the Hausman test is revealing problems, inconsistency of the estimator by GLS, and therefore we should estimate the random effects model by the covariance estimator. And so that is the idea. The idea also is that under the null, the test would not reject, would have a small value, and that small value would signal that there is no correlation or little correlation between alphas and x's, and therefore the GLS estimator would be consistent and efficient, appropriate for estimation. So that would be the idea. We are going to go back to the Hausmann test and make practice with that. But right now, let's continue with the part of theory. And we are going to look at variables that have no variation across time for one or several individuals, for all the individuals. In this case, we have individual specific variables that are the z's, z sub I. Those variables only vary across individuals but do not vary across time. So this is a typical case of the gender of a person, of the race of a person, of the place of origin of a person, things that do not change a long time. In this case, we have a problem here, because if we use the fixed effect model and estimate it using the covariance estimator, we would have perfect collinearity, and what Stata does is that it drops those variables from the estimation. So it kicks them out and estimates the rest of the model as if those variables did not exist. That we will see, because that happens all the time in practice with real data. Here in this transparency 41, we are looking at things that Stata does automatically for us, so we don't want to look at into this in detail, because Stata does it and we don't know exactly how. And the same goes for transparency 42. Those things are done automatically. The idea is, basic idea that Stata does is estimates by covariance and then substitute in the formulas to estimate gammas and mu's. But again, those are not necessarily important for your applications. And another idea here is, again, the same when the effects alpha sub I are random. So when we are dealing with a random effects model and uncorrelated with x's and c's, then the covariance estimator is not blue. It would be better to estimate using generalized least squares. So this goes for the previous case in which there are variables that do not change a long time, and in this case you can estimate them by covariance, but some of them are missing, or by generalized least squares, and that would be the best choice in this point. It is important the interpretation of the model that has variables that do not vary across time, and the interpretation is that those variables are included in order to explain individual effects, and this allows to eliminate the correlation between individual effects and regressors. So they are important variables, not something that you want just to drop easily. Let's look now at yet another variation of the model, and another variation of the model is, if you look at the model up there, y it equals mu plus z prime I gamma and the rest of the formula, you will see that it is essentially the same as the previous one, except that now you have some more time components. You have lambda t and you have the r prime sub t. Those are things that happen unchanged only a long time. They don't change across individuals, only a long time. The lambda time effect would be something that happens to everybody in an economy, for instance, and it may change a long time, but it's the same for all the individuals at a given point in time. It's like an increase in interest rates, or an economic war, or situations in which there is a crisis, devaluation, anything like that. And the same goes for RT, but those vary also and are observable. Now let's see what we can do with a model like this. In principle, you would do something very simple. Use Stata, put your data on, use Stata, and don't worry because Stata is going to estimate well. If you use the fixed effects, then we cannot estimate all the parameters. If we use random effects, we can use an estimator in several steps, and if the random components are uncorrelated with R, Z, and X, we would use generalized least squares. So in principle, this is similar to what we have seen. And then to finish with, let's talk about heteroskedasticity. You know already from previous courses that heteroskedasticity is a problem with the data, sometimes also a problem in which in the way in which a model is constructed. And the idea is that the units have different sizes, and that causes that the variance of the error is different across different individuals. That is a problem, that is a second order problem. And in the case of the error components, it may arise because the alphas vary with the size of I, and this is a problem which is typical in econometrics, heteroskedasticity. Heteroskedasticity again is different precision of the model for different individuals. The individuals being cities, countries, firms, whatever. The typical reason for heteroskedasticity is different sizes. So if you have different sizes of cities, of countries, or regions, whatever you're dealing with, that typically causes heteroskedasticity. And heteroskedasticity is not a terrible problem, it's not a first order problem, it's a second order. It's a problem with efficiency, but not necessarily with consistency. So let's see now what we can do with heteroskedasticity. The heteroskedasticity is typically present in panel data, and that is something that we have to be aware of because this is the typical situation. We may not want even to test it, but we want to correct it in general. Here, starting in page 48, you have some explanations of heteroskedasticity and ways to correct it. These ways to correct it are correct, are precise, are useful, but nowadays they have fallen into disuse because there are automatic procedures which work very well and which are supposed to be like the standard in applied work. So we more or less skip this part of the formulas, and the idea is that you can certainly correct for heteroskedasticity if you knew the form, but in general you don't know what is exactly the shape and the cause of heteroskedasticity. So typically you want to use a general formula for correcting for heteroskedasticity instead of a very specific model of heteroskedasticity. Nowadays we prefer to use a modern treatment of heteroskedasticity, which is associated with Albert White, who was my PhD advisor at the University of California, San Diego. He devised a test that is called the White test of heteroskedasticity, that you will probably know from previous courses. This is an omnibus test that checks for any damaging heteroskedasticity that may be in the data and in the model. And what he does is to propose a heteroskedasticity consistent variance covariance matrix estimator, and based on that he can propose estimation and inference that makes sense even in the presence of heteroskedasticity. In practice, this is done automatically by Stata. You just have to use the right option. Sometimes it's a VCE option, depending on which estimation technique you are using. It is important to use it always in applied work, always. Never forget about using the automatic heteroskedasticity correction. There are several options that you will see in Stata, and the interpretation of the model and coefficients is exactly the same as before. You have exactly the same point estimates of the coefficient, but different t values and p values. Okay, so now we are ready to go to the practice in Stata using real data. Thank you.